All right, so we've already talked about some of our calculations, how to draw waves, and then we also need to look at interactions. So how do waves interact with one another? What happens when waves strike a surface? Do they reflect, or do they enter that new medium and refract? So some of these words you might have heard before. So for example, reflection, you guys know what reflection is, right? You look at yourself in the mirror every day probably before you leave school. No? There's your reflection, right? Well, you're seeing that image because the light's striking the mirror and bouncing back and going to your eyes, right? What type of technology does our Navy use? Sonar, right? Bats. How do bats know where to fly in the dark? Echolocation, right? Those are all due to reflection, okay? So if a wave bounces off a surface and comes back, we can kind of use that information to judge where things are. Refraction, if you put a pencil in a cup of water, what does the pencil look like? Looks like it's broken, right? You guys all seen that one? You've never seen that one?
Yeah.
I was like, come on, I know you have. If not, I will grab a cup of water and we will do that one together. But it appears to be broken because the light waves are now entering a different medium. Originally, the light waves were up here, which was our air, and then the light waves pass in here, which is the water. And when that happens, it causes it to bend either towards or away from normal based upon the medium you're entering, whether it's more dense or less dense. The last one would be diffraction, which is where your waves are going to spread out as they pass through a small gap. Okay? Can you picture like a cheerleader's megahorn thingy? What do you call that? You know what I mean though, right? When they talk through that, what happens? How does it sound, louder or quieter? Louder, because those waves are focusing their sound waves through a small opening, so then it spreads out and hits more people or more fans as they are cheering for their team. Go Jets, right? So law of reflection says as a wave strikes a surface, whatever angle it strikes the surface with is going to reflect off at the same angle. Okay, so if you look, this theta, if I strike the surface at 20 degrees, how many degrees will I be reflected at? 20. They're going to be the same. So reflection, as it strikes, it's going to bounce off at the exact same. If I hit it at 90 degrees, it's going to come right back to me at 90 degrees. Right? All right, so sonar is a great way for us to be able to gauge how far something is, where other submarines are, where there's other objects, things like that. So we have echoes. And so if we know the speed of sound in water and we send out a pulse, it's going to go down, strike that surface, and then it's going to come back. If I can hear the echo, that is the time it takes to go down and back, right? Would I want time for it to be down and back? Or if I want to know how far away is it, do I just want the time down? Just the time down, right? So all I would have to do is just divide that time. So you got to be really, really careful with the ones that talk about echoes, because the question is it down or is it down and back that I need? All right, so take a look at this one. A woman screams when 100 meters from a high wall. So here's the lady, smiling, but there's a big high wall there. She's going to scream. It's going to hit the surface, and it's going to come right on back. Okay? What time of delay would there be before she hears an echo? All right, so she's 100 meters from the wall. What time delay will there be before she hears the echo? If I want to hear it, is that time down or time back? Or down and back, I guess I should say. down and back, right? So I want down and back. So if she's 100 meters from the wall, what total distance does that wave have to travel? 200 meters, right? So if I use my equation, speed is distance over time, and I rearrange it for time, I get that time is distance divided by speed, right? So the distance is 200. The speed, it says the speed of sound in air is 330 meters per second. So I just have to divide it by 330. So 200 divided by 330 is going to give me 0.6. Now it's time. What would be my units be for time? Seconds, yeah. Seconds. And that's it. Okay? So these ones aren't too bad. It still uses that same equation we used to use back in the day, that distance is speed, speed is distance over time. And then you just solve it for time, or you could solve for distance. But you got to ask yourself, am I looking for down and back, or do I just want down, right? And go. All right, interference. So there's two types of interference, constructive and destructive. If I'm your coach and I'm trying to give you constructive criticism, am I trying to build you up or tear you down? Build you up, right? So if waves are interfering and it's constructive interference, do you think that would make the sound louder or quieter? Louder, right? It's going to amplify. When it amplifies, it's on the same pattern. So they're both heading up on a crest, or both waves are coming down into a trough. Okay, they're on the same pattern. So if you look over here, you see how they both are going up and then both going down at the same time. That's going to give us a bigger amplitude. Or, like earlier today, once everybody started talking and talking and talking and talking and talking and talking, it just kept getting louder and louder and louder, right? Whereas, think about destructive. If you're destructive, you're going to tear something down, right? We use destructive interference all the time. Think about like a recording studio, or in the band room, or anything like that. Do we want the sound to go out to all the other rooms, or do we want to cut down that sound? We want to cut it down. We want to stop that sound. So when that happens, destructive, they're on the opposite patterns. One's going up and the other's going down. So they either will 100% cancel them out and come back to rest, or they'll just form a smaller amplitude. Okay, so you have constructive and destructive. Constructive, destructive. So take a look here. What would happen with these two waves, right at those 2 points? Here and here. Constructive or destructive? Constructive. This amplitude is 2. This amplitude is 4. What do you think the new wave is going to be? 6. So my new wave, when it interferes, is going to look like that. Boom. And then same thing. They're both on the same path. Down. So that blue line that I just drew would be our constructive. All right, take a look here. This is where it gets a little bit tricky because they have different frequencies. Some parts, like let's look right here, constructive or destructive? Constructive. But what about here and here? Destructive, right? So it would cancel out or make us a smaller wave. Okay, so again, if they're on the same pattern, they're both going up into a crest or they're both going down into a trough, it'll be constructive. If one's going into a crest and one's going into a trough, it's going to be destructive. Okay, that happens because of this principle, the principle of superposition. So when two waves interfere, the resulting displacement of the medium at any location is the algebraic sum. So we just did 2 plus 4 to get the resulting amplitude of 6. Does that make sense? So let's say I had 6 as my amplitude and I was going up on a crest, and I had 4 going down on a trough. 6 minus 4 would give me 2. So the resultant amplitude would just be a little 2, right? So they're actually going to either cancel out or add together. One other wave impact that you guys know of is what is called the Doppler effect. We talked about this back when we talked about whether the universe was expanding or not. Remember, this was one of our evidence that redshift was happening. The wavelengths were getting longer and longer. They were moving away from us. Whereas if it was blue shifted, the stars would appear like they're getting closer to us. And so I would have a higher frequency, shorter wavelength. With an ambulance, when that ambulance comes close to you, when it comes close to you, does it sound like a higher frequency or lower frequency? Higher, because as it's coming close to you, those sound waves kind of bunch up. Has the actual sound being produced by the ambulance actually changed? No, but it's an apparent shift, right? So as it's coming towards us, because that ambulance is moving and I'm standing still, it sounds like a higher pitch. Once it passes my car, it gets lower pitch, right? Because now the waves are moving away from me. So it's an apparent shift. The actual sound being produced by the ambulance has not actually changed. So this came back in from when we looked at our tuning forks. A higher frequency tends to have a higher pitch, lower frequency, lower pitch. Okay? With diffraction, these relationships is what you're going to be looking at today. Okay? So with the gizmo, you guys are going to be taking a look at the gap size. So if that gap size is equal to our wavelength, then I will see maximum diffraction. Remember, diffraction is when I have that megaphone, right? And I'm yelling through it, and it sounds louder. I'm trying to amplify it, spread the waves out a little bit more. So if I change the gap, let me show you a picture. So do you see how this is a bigger gap here and a smaller gap here? Well, a bigger gap isn't going to spread the waves out as much, but a small gap will. So that megaphone where you actually put your mouth, it's pretty small, right? But then the opening at the end is really large so that those waves have room to spread out in order to the fans. So here's another picture for you where you can actually see them spreading out a little bit more. All right, so a couple key points to kind of just wrap up here at the end. When we look at waves and we say, okay, waves, how are they going to behave? They do have certain frequencies. They do have certain wavelengths. Those are their wave properties. But if I have multiple waves, they can interact. That can have constructive, destructive interference. When that wave has to pass through a small opening, it happens the exact same way. So as I'm talking right here, I'm producing sound, right? Now, can somebody that's not in my classroom around the hallway, down the hall, hear me if I'm really, really loud? Yeah, because it can bend, it can move. Those waves are not stagnant. So these interactions are some of the things that we are going to be looking at for today. Just again, another reminder, because this was our big takeaway from Monday, wave speed is only dependent upon the properties of the medium, not on the properties of the actual wave. And then there's a couple of videos that I had linked throughout. If you guys want to watch those, they're extra resources that you guys can use. Okay?